Hey, welcome back. So the last videos were a whole lot of talking, so I figured it's time to make something again, and I needed one of these anyways. This is a specialized shallow bore gauge or also a dual contact taper gauge. And I need this to machine my own backplates for the lathe. Let me show you why you need something like this. Otherwise, making those backplates is a whole lot of pain. That's the spindle nose of my lathe. It has a Morse taper 4 on the inside, shortened Morse taper 4, and it has a number 4 short taper on the outside. This is the same taper that you would find on a D1-4 camlock spindle, but the mounting system is different. Instead of camlock, it uses a through bolt and a bayonet disc behind it. But the taper and the whole design of the taper is the same. This is a very short and very mild taper. It's 7 degrees, 7 arc minutes and 30 arc seconds. And the way this works is the taper will make contact first, and there will be a gap of about 10 micron between the face of the flange and the backplate that you're mounting, or the chuck that you're mounting. And once you tighten the mounting bolts, it pulls the backplate into the taper in the backplate expands a little bit. Everything is elastic. Remember, everything is rubber. It squeezes itself onto the taper, and the face will make full contact. That creates a super rigid connection between those two parts. It's also extremely repeatable. In addition to that general repeatability that's already built into the system, there is also an index screw. This is just a regular M8 screw, socket cap screw, and there is a large counter bore in the backplate, so it can only go on in one of the 3 orientations. So if you machined the backplate on this machine, it will always go on in the same orientation with the same error that the machine put into the backplate, giving you an ideal axial and radial runout. I want to try to show you the 10 micron gap between the backplate and the spindle nose. So this is my 4-jaw chuck. And I'm leaving the bolts loose, so I'm just holding it up by hand, and I will move the camera so you can see the gap better. Okay, that's the gap between the spindle and the backplate, obviously. And when I push these together, it's already very hard to see. There you can see a little bit of the gap right underneath the flashlight. And when I take a piece of 10 micron shim stock, you can see how this goes between the backplate and the spindle. So I lock the bayonet ring. When I tighten these 3 nuts now, doesn't take much. If I was going to machine something, I would tighten them a little bit more. But just for this demo, this is tight enough. And now when I try to fit the shim stock in here, well, good luck. It tightened up against the face. It's making full contact now, and it's a solid, rigid connection. So that's the deal with these short taper spindle noses. That's what they are called here. We call that a short taper number 4, Kurzkegel number 4. And normally, on a really good fitting short taper backplate, when you tighten the nut, when you loosen the nuts, the chuck will be stuck on here. See, it's on the taper and it's seated. It's like a Morse taper that's hammered into its socket. So usually you take a soft blow hammer. I prefer rawhide. Give it a tiny tap. Make sure the bayonet disc back here is disengaged, and then it comes off. What's the deal now with these short tapers and this gauge that I made? Well, the diameter of the taper is the problem. Since it's a taper, you cannot just go in there with, for example, calipers and measure it because it's on a taper. You need to measure or compare the diameter of this tapered bore in relation to the face. And that's what my gauge does. This is not my idea. Alex, the engineer's findings, if you're not subscribed to him, you should absolutely, because he is a proper engineer and an incredible good machinist and an incredible good welder. He built something very similar as a welded design, which is a fabulous, simple construction. I'm not a very good welder, so I machined this thing. And the idea is you have 3 contact points that sit on the face of the back plate. And you have 2 contact points down here that sit about halfway down on the taper, making contact. And then you have a third contact point, which is the dial test indicator, also about at the same height as these contact balls down here. So the idea is you have those 2 contact points and you drop this gauge into the taper bore, making 3-point contact on the flange here. You push it up against the back side of the gauge where the 2 points make contact, and you will get a reading on the dial test indicator in front here that gives you a relative measurement to whatever you use to zero this out. This is a comparative gauge, so you need a master. In the easiest case, that's a known good backplate or chuck that you already have. I mean, if you have a lathe with a certain spindle nose, you have probably at least one chuck that fits it, and you can take that as a reference and make assumptions from there. Depending on how tight the backplate fits, you know, I have to adjust maybe 10 microns either direction. So the idea is to zero it out on a known good flange. Try not to bump the dial test indicator. It's a delicate instrument, that's for sure, but it works fine. There is the comparative reading. So let's look how I made this thing. Here's a sketch and a dimension drawing for the base plate of the taper gauge. Material will be 10mm cast aluminum plate. I think spanning across the bore of the short taper, that will be plenty stiff. It doesn't need the super stiffness of steel. Aluminum will do fine, I'm very certain here. The contact points will be steel anyway. Hey, in 2 years I did not manage to cut off the linear rails of this sliding saw table. I removed the clamp because I'm cutting plate. And I added a stop so it doesn't move all over the place. There we go. Plate is squared up, picked up my zero, drill chuck, ready to go. By the way, the drill chuck, this is a 6.5mm Albrecht drill chuck on a 10mm shank in combination with a 10mm edge finder and with a 10mm end mill. This is a great combo of just making plates with holes. End mill for squaring up plates to a certain thickness, of course. Edge finder to find your zero, and the drill chuck to drill. Kind of a rather efficient way of doing things on a manual machine, as far as manual machines go, because you don't have to swap around collets. We need to drill 2 bolt hole circles. One with 3 holes and one only with 2 holes. Start with the inner one. Those are through holes, diameter 5. Let's set the DRO. We have X and Y 0. And we have a diameter of 57. We need 3 holes, but we have a starting angle of minus 90, I think. Well, the other minus 90. That's better. And let's start. We want those 2 holes only. We just crank to 0. And drill and ream them. These are not really precision holes. Since it's a 3-point support, it's the actual position of the contact point doesn't really matter that much, within reason. I'm spot drilling all the holes, just so I see that I'm not doing anything stupid. So we have 3 ball bearing balls pressed into bores in these 3 spots, and these 2 here will be drilled through, and they will have basically ball bearing ball on a stick. You could of course use a commercial tooling ball with a stem, but those are kind of hard to get here in Germany for some odd reason. I think Misumi sells them, but I'm not really sure. I don't know what the deal is with those being rather hard to obtain. We'll pre-drill. The bearing balls are, what are they? They are 6.35 millimeters, quarter inch. I think I scavenged them out of a bearing. So I will drill 5 millimeters deep. Now the question is how to big to drill them for the bearing balls. I would like to put them in with a very light press fit at best. This is a well sharpened 6.3 millimeter drill. The question is, did it drill on size? Oop. Oh, hello. Ha, that's nice. That will be a mild press fit. The drill is 6.3. And the bearing ball is 6.35. That's the reason why I pre-drilled. Otherwise, the drill won't drill that precisely on size. Oh, I just noticed maybe I should drill to depth with the DRO of the mill. Just so they are all the same depth. That's a little bit more precise than using the dial on the quill of this machine. For everyone familiar with the decal mills, they know this wrench, 12 millimeter square. This is used for the tool drawbar, but it's also used as a quill handle. It's a perfectly fine solution. I did this for the last 10 years on several decal machines, well, longer than that. But on my machine, I have this guard that sticks out to the side and protects the y-axis ways from chips. So this always gets into a collision. So I played around with some designs for a quill handle, like a small wheel, 3-spoke design, but then I looked at the Decal FP2, which has a horizontal quill, which is a really cool design feature. FP2, 3, and I think the 4 all have a horizontal quill. Means you have about 150 millimeters of quill travel for drilling. And the quill handle has 2 spokes and is relatively small. And I copied that, and it looks like this. This is a 3D print, of course. The stems here are just M8 screws, socket head cap screws, with a 3D printed ball pressed on the end, screwed into a 3D print. The square is 3D printed. And this is honestly it's the ideal size for a quill handle. It's long enough to give you enough force for drilling, like even larger drills like 10, 15, 20 millimeters, or core drills. But also, when you grab it like this, well, I'll show it differently. When you grab it like this, you have a ton of fine feel and precision to feed it. And if you want to move it very quickly, you can use your palm of the hand. At some point in time, I of course want to make a steel version, because this is kind of a Mickey Mouse thing. I'm not a huge 3D print fan. Sorry, forgot to turn on the camera. I milled the slot where the dial test indicator will poke through the plate. Just with a 10 millimeter end mill, plunged it out and cleaned up the side walls. It is annoyingly close to the contact point here, but there is still material left, so it's fine. I want a little bit of a slot here. Well, yeah, a slot, like a shallow slot to guide the holder for the dial test indicator, so it's not flopping all over the place, and I can just fix it in place with one screw. So I milled, again, forgot to turn on the camera. This is becoming a recurring theme here. I milled a slot here, and I think it should be wide enough for this piece of precision ground flat stock that I'm going to use for the dial test indicator holder. So let's see. Yeah, that's a sliding fit. Perfect. But I think I want it to be deeper. This end mill has quite a bit of a chamfer on the edges. That's a 2 millimeter deep slot now. This gives me enough guidance in life. Let's change the drill chuck, poke 1 or 2 threaded holes in there. And to give you an idea what's going on, the dial test indicator will sit about here. It will be slightly adjustable in this direction. I have some major adjustment by moving the stem of the dial test indicator So everything will be fine. So part this out of the vise. I want some set screws from, oh, this is nicer, from the back side that will hold these ball bearing balls on a stick in the body of the jig or gauge. A end stop would be nice. You might remember these precision ground magnets. Made these almost a decade ago. Still super useful. Would make them again in a hurry. Oh, and I put it in wrong. That's funny. Like this. Let's find the center of this hole. Instead of moving back and forth, I can just flip the part. Let's do some layout to cut off those ears. I prefer just a paint marker over die-chem in a bottle. Usually that's fine for what I do. So this is 85. Half of 85 is 42 and a half. 42 and a half. So I moved the caliper to 42 and a half. Zero it in this position. Idiot check. Yeah, that's in the middle. And I want two lines 6 millimeter from center, so I put it to 6 millimeters. Align it with, line the moving jaw up with the edge of the part. I have my carbide scribe here. Just strike a short line here, short line here. Going back to 0. I want to go 20 in from down here. Oh no, you can't do that with calipers. Well, I very much can. Steel scale. Lining the ends of those lines. Pulling a line. This is a 2 millimeter lead holder, like you would use for drafting. And I took a piece of 2 millimeter carbide stock, tungsten carbide, ground a nice tip out and polished it with 1 micron diamond on an old CD. Gives a very, very nice scribe. So that's the 2 ears that we want to cut off. And also we want to cut off those ears down here. Let's make those blue too. Let's do 12 millimeters. This is a relatively precise method of doing very, very quick layout. Works very well in sheet metal, for example. And it's not as evil to the calipers as the other method. You can, of course, also just do this and scribe lines like this. I will do that, but it's it's hard on the caliper. Don't do it with your nice set that you're using every day, or expect some damage. So let's go to bandsaw and remove those two large pieces. The small ones I will mill completely. Yeah, this bandsaw blade has its best days behind it. We want to clean up those sawn surfaces, and for that I will just hold it at an angle in the vise. But how to align it? Well, that's easy. Just find two parallels that are approximately the right height. Then you just align your scribed line with the top of the parallel, clamp it. There we go. I really like this method. I can exactly tell you when and where I learned this during an internship at, funnily enough, at Siemens. The apprentice instructor showed us exactly this method, which is kind of a wild thing to show to interns who we had no clue what we were doing. But I never forgot this thing that he showed us, and I use it always since then when I have to do a quick angled cut. Cleaned it up, cut all the chamfers. These could be a little bit smaller. They kind of go very close to the edge of these contact patches, but it's fine. So time to press them in. Ball bearing, piece of aluminium so I don't Brinell my bench vise. Whoop! Oh, that went easy. That went in very nicely. Let's see the other one. Whoop. And the last one, just holding them in with a second piece of aluminium and pressing them in. Really not very problematic. That way we get nice, hard and smooth contact points. Hardened dowel pin. And this is a 6mm ball end mill, carbide, running at, that's 205 RPM. There we go. That's a bit of a spherical pocket. Add a little bit of solder for flux. Drop the bearing ball in. heatsink. And yeah, that wetted. There we go. Off to the lathe for a little bit of cleanup on the discoloration back here. Of course it doesn't run true perfectly, but it does not need to. I just need them to be static contact points, and I think they came out quite nice. Clean the pins up, and it's time for a little bit of sub-assembly. I have some set screws with a flat point on them. You wouldn't want a pointy set screw here, absolutely not. That would dig into the even into the hardened dowel pin, but a flat set screw is fine here. The height of these pins can be adjusted, and this determines the contact point in the taper. I already figured it out. I want it to be about 8 mm, so I have an 8 mm gauge block on my magnet here. I just put the gauge block on the thing here, and well, that's it. That sets the height of the pin to exactly 8 mm. Well, good enough, 8 mm. There we go. That's the pins. Let's tighten them to a defined neck. There we go. Looks already like an instrument. And here on this old backplate, you can see how this works. The two pins drop inside the tapered bore, and the three ball contact points sit on the face here. The two defining features of a short taper spindle nose. And if I flip it around, you can see how the two pins make contact. I've sawn a piece of the precision ground flat stock off, and this is obviously parallel, and this is also parallel, and it's kind of square-ish. It's not really square, but good enough for what I'm doing here. But I want the sawn ends, of course, to be square with both of these sides. So you could hang it out on the side like this from the vise, or you could try to stand it up like this and orient it like this to square it up. But there is a really neat trick that creates the precision end itself, and that we start by putting it in a vise like this, and you really only eyeball it square. It doesn't really need to be square. So you clamp it like this. And what did it give us, apart from me cutting too deep back here, which we'll clean up later? It created this surface which is square to these ends. It's not square to the large faces here, but with the next step we will fix that. And now the surface that we just milled with our little blemish drops on the parallel. This gives us the squareness in this orientation, and the vice jaw against the large face gives us the squareness in this orientation. So the second side that we're now cutting is already completely square to the other faces. And now we flip it and surface the other side, which is only square in one orientation. We surface that to final thickness or final height, depending on how you want to think of it. That 3-point squaring method is also something that I learned very early on in my apprenticeship. And that I used all the time afterwards. It's a super useful technique if you don't have any special squaring tools. So measuring my final height, this is 22. So we need to remove 2 more millimeters here. Squared the little block up, the little block that could. Before I start to cut away more material, I will do all the work here in the end, means cutting the dovetail for the dial test indicator. Slotting out the majority of the material with a 3mm end mill. Now changing to a miniature dovetail D-bit. I have shown in at least the half moon dial test indicator holder how to grind one of these yourself. So I'm not going to show it again. Here is the cutter. Just ground on the end of an old carbide end mill. Running at 2000 RPM. This will do very, very fine. Something else about these dovetails, don't make them ultra tight, because dial test indicators have quite a little bit of variance in their dovetail tolerances. Let's see, it's the second one of these. Yeah, that one is looser than this one. Same manufacturer, same series of test indicator, but different fit on the dovetail. So be a little bit careful on that and plan for some squeezability in your design. So there is a third. Yeah, this one is also rather loose. Let's check. This is a different manufacturer. This is a Mar. And whoop, that's extremely loose. So yeah, tolerances on these dovetails on the dial test indicators is all over the shop. So maybe this clamp design is not the best in the world, but I kind of like it because it's ultra robust. Drilling and tapping the clamping screw going for M4. That's the tap drill for M4. Clearance for the upper half of the clamp. And the M4 tap. There we go. So I spent some time with die grinder and Scotch-Brite to clean the dial test indicator holder up. And all that's left is to put it together. The base plate with the balls, you have seen me adjust these spherical contact points to the right height, locked in place. Now we have the sliding element here. Also, off camera, I turned a nice heavy washer out of brass because this thin commercial off-the-shelf washer just didn't cut it. So, tiny dab of molybdenum disulfide grease on the screw because we're directly screwing into aluminium. And a little bit of lubrication on that end. It doesn't hurt. If this was a permanent tool that I used all the time, I definitely would put either a helicoil or a solid threaded insert in the base plate, or make the base plate out of steel. But for a tool that will see very, very little use, I think the aluminum base plate is perfectly suitable. Clamping screw and the dial test indicator drops in. And we adjust the contact point to be about the same as on the large spheres up here. Doesn't really matter, it won't hurt if that's not exactly the same height. But to make it a little bit nicer. So yeah, that's the finished shallow taper gauge, I guess. So let's see how this works. I have this old scrap backplate with the short taper number 4 in it. And first we need, and I can use that as a 0 because the taper is in good nick on it. So we drop the gauge in here. The 2 contact points rest against rest against the taper. Ugh. Now it's just a matter of adjusting the dial test indicator until it makes contact with the wall of the taper too. Yeah, I know what you think. Stefan, a fine adjuster would be really cool here, but see how well this can be pushed into position without a fine adjust. Really not a big deal. You move it roughly in position, like close to 10 micron, then you just zero the dial. You tighten it, make sure it's seated nicely, and then you boop, zero. There's your fine adjust. There we go. And it's nice and repeating. What I think is quite nifty about this design is that it also fits into the backplate with the 3 studs installed. There is even a little bit of wiggle room to make sure it's nicely seated. I'm zeroing out the gauge on this backplate. Now I can check the other ones or compare the other one. You have to be a little bit careful so you don't bump the dial test indicator, of course. But it's quite easy to get this into the taper by starting it on the back and then just tilting it downwards, and that will very gently put it in place. And you can already see that it's not zero. The indicator gets actuated more. That means that the taper is a little bit smaller on this one compared to its relation to the face. And I can confirm that because this backplate sticks a little bit more on the taper of the lathe than, say, my 6-jaw. Let's compare it to the 6-jaw. Let's put it in here. And here we have a 5 to 10 micron larger taper than on the master backplate. That also confirms what I already know. This does not stick on the short taper. In reality, I would have to remove a tiny bit of material from the face of this backplate to make it really a true dual contact, but I never felt really the need to do it because it is on the edge of sticking, and that's fine. But yeah, this confirms what I already knew, but with a number to it, so that's nice. And also this confirms that I didn't build a useless measuring device. Well, it's kind of useless because, well, not useless, but it's very single use or single purpose. I'm machining a backplate here out of ductile iron. This is GGG40, and the stuff machine is really nice. It, as the name implies, it's ductile compared to something like gray cast iron that's very crumbly and very rather brittle. That's the chips I got from boring the ductile iron, the taper here. Yeah, I took pretty heavy cuts here. And yeah, it makes a nice curly chip. And it's not as dirty as gray iron. Really great material to work with. It's still dirty, but way less than gray iron. And our almost finished board, the taper. Let's bring in my gauge and see where we are. I zeroed it on my good backplate, dropping it in here. And we are 40 micron undersize. That's good. I did a finishing pass on the taper, and I got it to fit quite nicely. It's about 5 micron on the tighter side compared to the backplate that I'm using as a master. That's nice. That's nice. My master backplate is a little bit on the not so heavy fitting side. This will be a slightly tighter fit on the taper. Let's see how it fits. Okay, it seats on the taper first, definitely. Otherwise, it wouldn't stick to the spindle. See, if I push it on, it stays there. That means that the taper is bearing first. Taper being 7 degrees and some change means it's self-locking. And when I take some 10 micron shim stock, oh yeah, very nice. Just poke in some holes and then I can mount it. And here the newly made flange is in place. It's used to mount a 3R Mini hydraulic chuck on it. The 3R Mini system is a 0-point system that was originally designed for RAM EDM machines and electrode machining. So you would machine the electrodes on the system, and you could transfer them between machines for grinding, turning, and milling. Then go to the EDM machine to burn your feature into your part without losing your 0-point. Because I don't have one here yet. The holders have a 20mm shank that gets held in the 20mm bore of this chuck. And they have a cross pin which registers against this single pin here on the chuck to give your rotational alignment. And this is a highly repeatable system despite being very simple. I'm planning on using this to move all my very small parts, high precision small part work onto this system because it's way more suitable for the lathe than the Irova system that I use on the CNC mill. So, well, there goes another standard in my shop. I have now the Lang system, the Irova system, and the 3R. Some of it is curiosity, some of it is... Now you might say, well, just put the darn tool in a 20mm collet. Yeah, that's true, that's very similar, but these hydraulic chucks are way more repeatable. We talk repeatable within 3 micron on runout compared to a standard collet that is more in the repeatability of 10 micron. Things add up quite quickly when you do very small parts and you have to change between machines. So I have the hydraulic chuck on here, and I also made one for the decal mill. Well, I made a flange for another hydraulic chuck to go on the indexing head of the decal mill. And this is even a 4-position one where you can index your work exactly 90 degrees. If you're not already running on an indexer. These chucks are runout adjustable on their back plates. So you just come in here with an hex key and you have 4 radial set screws moving the chuck around on the back plate, just like an adjustable a set-through chuck on a lathe. And if you wonder what the holders that go into these 3R hydraulic chucks look like, it's this. Just a straight shank with a cross pin here. The cross pin is for the rotational and the height reference. These come usually as a soft-ended blank, and these are used. The company that used these beforehand had them threaded with a metric M10x1 fine thread, and I suspect, since they come out of a mold making shop, they screwed on either graphite or copper electrodes for RAM EDM. They have this groove on the back. You can put an O-ring in there. Some of them have an O-ring. And you can drill through to flush through the electrode. You would have the same hydraulic chuck on your RAM EDM machine. So you can take this out of one machine and the other, do another machining process, go to the next machine, and then put it in your EDM and do your sparking. This might look very abstract because, well, it's a stick with a cross pin. But the idea is really, really well working. What I'm currently dealing with is, I made a holder to hold these parts to be machined on a lathe and then transferred to the milling machine to do additional machining there. So, and I might show this as a little bonus trick. So I took one of the 3R blanks with threaded end. I made a little screw-on head and I machined it to be a precision bore on these parts OD. So super tight fit, less than 10 micron side-to-side play. But how do you hold the part? Well, normally you would put something like, you would slot it and pull it together like a collet. But if the fit is that close, you don't need the slit. You can just use a shaft collar like this, the split type. Put this over here. And the part goes in here. And the shaft collar collapses the bore far enough to hold this super securely for all kinds of machining operations. And this is a very repeatable solution to make a kind of a collet solution without having to make a real collet. It works very well for small parts. And to get the part out, you just loosen it and pull it out. I machined the bore with precision floor. I faced the floor of the bore, so this goes in. Each of the parts goes in to exactly the same depth when I change them, so I don't have to do constant touch off when I go to the next part. So that's rather nice. And this is working very well. Okay, here is a close-up of the business end. This is 3.8mm ID bore and a 5mm OD. 0.6mm wall thickness. And the shaft collar here is, of course, also same 5mm diameter here. Part goes in. And I use a torque screwdriver, 1 Newton meter. And this is going nowhere. See, when I tighten it only a little bit, it already collapses the bore far enough to hold it. And that's like, yeah, I don't have a torque wrench that goes that low. 1 Newton meter is the weakest torque screwdriver I have. But this is far from 1 Newton meter. So it doesn't really take to collapse a bore in this manner. Okay, finished boring. This is a 2.6mm gauge pin. Fits down all the way to the bottom of the bore. And this is a 2.61, 10 micron oversize gauge pin. This doesn't even start, so that's within tolerance. And from there, I can take my fixture, loosen the hydraulic chuck here, pull the fixture out, walk over to the milling machine, and this drops in straight here, goes up against the register pin, and gets locked in place down here with 2 to 2.5 turns on the set screw, inflating the hydraulic bladder in there, clamping the straight shank of this fixture in place. And now if I wanted to go to a third machine, take it out, oops, take it out, walk to, for example, surface grinder, do some spin grinding on it until everything is done, and then the part comes out of the fixture. In this case, the fixture itself is repeatable enough so I can swap parts in the fixture. That's what I'm also doing here. But I still have the benefit of having a very repeatable system of holding the fixture itself to the machine. Yeah, time to set this mill up to do this step here on these parts. These parts I'm making here are not the topic of this video. I want to show you why I made the short taper gauge. I made it to make the backplate to mount these hydraulic chucks on the lathe, so I can make these parts more efficient to pay for cat food. So it's a wonderful circle. I hope this little build project was helpful to you. Maybe it's inspiration to design and build your own metrology tools for special purposes. Maybe you need a short taper gauge, so feel free to use this design. I hope you enjoyed. Thank you all for watching. Thanks for your support, and I'll be back.